In this video, we're going to study the chain rule in a higher number of dimensions. But first, I want to look back at the chain rule just for single variable functions. That is, I imagine a composition f of g of x. And both of those functions, f and g, were a function that has single input and a single output. Then what the chain rule would say back in Calculus 1 days was that the derivative of this composition was the derivative of the outside, f prime, evaluated at the inside, that's evaluated at g, and then multiplied by the derivative of the inside, multiplied by g prime of x. I could also write this in Leibniz notation as df dx is the product of two things, first df dg, and then multiplied by dg dx. Indeed, Leibniz notation is really useful when you have a whole bunch of different variables going around, which is exactly what we're going to have in the higher dimensional situation. So to look at one of these higher dimensional situations, let's consider the following. Imagine I have a function f, and the function f depends on an x and a y. So this is a function with two inputs, x and y, and a single output, w. But both the x and the y themselves depend on some other variable, t. Now, what's key here is that the x of t and the y of t, these are both single variable functions. They have a single input t and a single input x or y, depending on which they are. It's only the f that is a multivariable function. Now, try to keep track of all of this pictorially, and things are going to get more complex as we go into the future. One of the things we can draw is something called a dependency diagram. It looks like this. The idea of a dependency diagram is it tells you how the variables are related. So right down at the bottom, I have the input, the t. And then what the t does is that as you change the t, the x depends on t and the y depends on t. And then as you change the value of t, well, the x depends on t and the y depends on t. So both of those are dependent variables that change based on the independent variable t. And finally, as the x and the y change, then the w is going to change as well because the w depends on the x and the y. Now, we can use derivatives to describe the relationship between these variables in the dependency diagram. For instance, if I look at what the derivative of x with respect to t is, well, the derivative of x with respect to t tells me that if I change t a little bit, how much am I changing x? That this rate of change is given by dx dt. Likewise, for y, there's a dy dt, and the dy dt tells me, well, how much is y changing for little changes in x? And notice that because x and y are single variable functions here, that they are full derivatives. I use the lowercase d for that, single variable derivatives. But now let's imagine the relationships between x and y all the way going up to w. Well, now these are partial derivatives. For instance, there's a partial derivative, which is the change in w with respect to x. And this says as you change x, which is only one of the multiple different variables that w depends on. But if you only change the w, then dw dx gives you the rate of change of w as you change x. Likewise, for dw dy, it tells you the rate of change of w with respect to y. So, in other words, my w is depending on sort of changes that are coming about going through the x branch of this dependency diagram, and changes that come about going through the y branch of this dependency diagram. So the final answer is very analogous to the chain rule, but it's a sum of two things. The chain rule is said to be that the derivative of w with respect to t consists of the sum of two things. The one is when you change with respect to x, and then you also multiply by the derivative of x with respect to t. And the second is when you take the change in w with respect to y now, and multiply by the change in y with respect to t. Note that in this formula, sometimes you're using the single variable derivative d notation, sometimes using the partial derivative notation. It depends on what you're doing. When you think about w and t, well, w is a single output and t is a single input. So w is a function of t. That is a full derivative, a full single variable derivative dw dt. But then if I look at some of the other components, like the change in w with respect to x, w depends on many different things. So it's a partial derivative of w with respect to x. To help interpret how this formula works and why it is the way it is, I want to sort of take a little bit of a zoom in and what these derivatives mean. Suppose that I take a small change in t, then what I can look at when I try to study the resulting change in x dependent on t, so if you change t, you're going to change x. When you look at what that small change in x that results, The value of the derivative dx dt, what that's telling you is sort of a ratio between when you change delta t a little bit, how much do you change delta x? It's the ratio between these things, or at least it's certainly the ratio as those values get arbitrarily small. Likewise, if I look at what the change in y is when I change delta t, that's what the derivative represents here. A change in the t variable results in a change in the y variable, and the ratio between those two things is given by the derivative dy dt. This is all fine back when we had a single variable, but if I look now at something like the change in w that results, well, w can change in sort of different ways. It can change as your x is changing, it can change as your y is changing. Indeed, you can think of any vector in the xy plane as being decomposed into the proportion that's a change in x and the proportion that's a change in y. So one thing you can express is as you change x a little bit, you get a corresponding change delta w, and that the partial derivative, the partial of w with respect to x, is the ratio between those changes. But that's just when you change x alone. If I then go and change y, I'm also going to get a change in w. That is, if I change my y, I have a delta y, then dw dy tells you the rate of change of w with respect to y. You get a change that comes from the y as well. Then I can take the delta x and the delta y, I can plug them in, and I get a change in w that's coming about from the changes in t that affect x, and I get a change in w that comes about as I change t and that affects y. And so the final result of my chain rule, which is that it is the sum of these two derivatives, in effect, I've divided both sides by delta t, I've taken a limit as this thing has gone small, and it becomes natural that you'd expect that the chain rule to be the sum of these two things. Now, when you look at this formula, it is what I will call a convenient fiction, that it appears that the dx on the top and the bottom cancels and the dy on the top and bottom cancels as well. Now, in truth, something like the change in w with respect to x is thought of as a single symbol. It's thought of a single concept, the rate of change of w with respect to y. So we're not exactly canceling. Nevertheless, it's convenient to remember chain rule that way. And indeed, this is a shorthand for the larger process of saying that we're going to be taking these limits and things are going to go to zero. We can make this more explicit and less hand-wavy. But the idea that they're canceling is a convenient fiction for us. There was nothing particularly special about just having our function depend on x and y. I can state the exact same kind of formula if your w depends on x and y and z and perhaps more variables. If you have more variables, you just keep on adding up terms like this. There is still a question of what happens if you have more output variables at the top row, the w row, or what happens if you have more input variables down at the bottom row, the t row, but we're going to investigate those questions in the future. The final thing we want to do in this video is just work through an explicit example. Here I've given a function, it is a f of xy, and it's the function x squared times y. But then I also say that x is a function of t, 2t plus 1, and y is a function of t, it's t cubed. So the w depends on x and y, and both of those depend on t. Now, there's actually two ways to go about this. One I'll just say in words. One thing that you could do is in place of the x and the y, you could just plug in those values of t, and what you get is some long mess in terms of t. Then you can take the derivative of that thing entirely in terms of t, and you'd get a result. That's one way you can do it. However, we want to practice doing this by the chain rule, and you can confirm if you wish that you're going to get the exact same result either way. So if I'm going to use the chain rule, well, let's recall what it is. Here, the change in w with respect to t is the sum of these two different things, and let's try to plug them all in. First up, I have the change in w with respect to x. Since my w is just given as x squared times y, when I'm taking the partial derivative with respect to x, y is thought of as a constant, just a number like 7, it just comes along. So the derivative of x squared is 2x, and I multiply by the y, that hasn't changed. Then when I take dx dt, the derivative of 2t plus 1 is just 2, so I multiply by 2. Next up, the partial derivative of w with respect to y. Well, if I'm taking a partial derivative with respect to y, now the x variable is not changing. And so what I have in this case is just the x squared, and then the derivative of y just goes down to 1, so nevertheless just an x squared. And then I multiply by the derivative of y with respect to t. If y is t cubed, then this is just 3t squared, and so I get this result. Now, this result is a little bit not presented in maybe the most ideal way, because there's x's and y's and t's, Anywhere there's an x and a y, we could just substitute in the equations for t and get our final answer entirely in terms of t. And so that gives us this long expression. So at the end of the day, the chain rule is not much more complicated than it was back in the single variable case. There's more terms and a few more variables to keep track of, but all the individual computations are just multiplications of different types of derivatives.